начать запись можно не нажимать.
Ну ладно.
Последнее, о чем мы говорили, что локальная конечность действия на Algebraic Groups.
Да. Но мы сегодня, кстати, об этом поговорим снова, потому что у нас будет некоторая теорема, которая с этим связана, важная, поэтому мы вернемся к этому. Дайте, то есть сейчас я начну немножко с другого, а следующим этапом я как раз буду отвечать на ваш этот вопрос. Напоминаю. So let me start. On previous class I was asked for a following, to recall the following theorems. So since it will be needed for the course, I want to do it. So semi-continuity of dimension of stabilizer and dimensions of orbits. Just if you have, so we start again with G will be algebraic group acting on algebraic variety. So here you want to consider the following. So you want to so you want to consider the following functions on the variety. That depends on the point. So the function just so the function phi that depends on the point, and it is the function, the dimension of the stabilizer of the point. So stabilizer. And we can consider the function, the dimension of the orbit, which is of course the dimension of the stabilizer minus dimension of G minus dimension of stabilizer. And so we will be interested how this, so this means that we are just looking at our variety. So you have collection of orbits here. And you consider, you take a point here, you consider the stabilizer, the orbit, and you ask yourself about these questions, what can be said about these functions. So the claim is, so since the talk is about semi-continuity, this will be about semi-continuity property. So that and of course it will follow from semi-continuity of the orbits. So let us recall the theorem of Chevalier that we will use today. So we mentioned that semi-continuity of fibers, of dimension of fibers. And so if you have morphism, so now you can state just more or less arbitrary this, so that the dimension of, so the function psi of x, which is a dimension of the fiber over the image of x. So I prefer to state it like this because, as you noticed, it was more convenient to state it on x, because the statement was true on x and wasn't true on y. That you take x on x, look at the f of x, and look at the corresponding preimage. And the claim is that the set on X where xn where well xk where dimension of the just in X of the fiber is bigger or equal than k is closed. Okay? So I want to study also these two functions and get something about their structure. Yeah, so of course it is doesn't matter which function to choose. Maybe since the stabilizer itself, it depends on the point. Yeah, so if you look at the orbit, yeah, so different stabilizers. So if you have x and gx, the stabilizers are of course differ by gx inverse. So they are conjugate, and this tells you that dimension is equal. So, but the stabilizers could be different. They could be just conjugate, but different as a subsets in G. So maybe it is more convenient to speak about the orbits, or more natural to speak about dimension of the orbits, because we will be more interested in the orbits as equivalent classes. But nevertheless, it will be more convenient for us to work with stabilizers. So this... Ну, просто смотрите, ну, как бы вот, ну, вот эта функция, как бы у нее с виду больше зависимости от орбиты, да, то есть вот эта функция точно постоянно на орбите точки, а вот эта функция тоже, конечно, постоянно на орбите точки, но по причине того, что стабилизатор точки Gx сопряжен с G, да, ну, что вы можете переписать его в таких терминах. Ну, поэтому, как бы, возможно, более правильно говорить об этой функции, как о более важной вещи, да, ну, и нас, вообще говоря, будут больше интересовать орбиты, ну, как множество, да, в многообразии. То есть мы скорее описываем орбиты, да, действия группы. То есть, ну, например, почему? Потому что, ну, обычно мы интересуемся какими-то классами эквивалентности, да. А классы эквивалентности, ну, то есть мы рассматриваем какие-то подмногообразия и рассматриваем их с точностью до действия группы. Ну, например, квадратичные формы с точностью до преобразования. Поэтому, конечно, мы больше интересуемся самим классом эквивалентности, а не как бы стабилизатором элемента там. Поэтому как бы правильно не, наверное, говорить об орбитах. Но это я просто так, это не имеет, просто философия, я бы сказал. Вот, so what can be said about, so now we have to somehow relate this function. Yeah, so of course usually the function comes, such functions comes from the action. Yeah, so if you fix a point here and you fix point in x, yeah, so yeah, so if you yeah, so the thing is that here you can consider the action map. Yeah, so if the stabilizers you have noticed, we can describe the stabilizer of x, yeah, as follows, as the intersection. So you have an action map rho of x. Yes, so you can consider the preimage of rho of x. So these are those elements that such g y such that gy is equal to x. Yeah? And you just, in order to calculate the stabilizer, you just intersect it with g times x. So you get the group that, so this is a closed subset in the group. Yeah? But notice that it is not convenient description because somehow the set of with which we intersect, it depends on x. So the idea is to reduce, so to consider the graph of the action. So graph of the action and the graph of the action is the following. So this is just so it is it is actually the unions of graphs for all elements of G, but we shall write it down in more convenient terms. So it is morally union of gamma of G, where gamma of G is graph of the action of the action by the element x. Yes, so you have a map between x into x that maps x to gx, and you are taking the unions of these graphs, and yeah, so yeah. So you are taking the unions of these graphs, and this gives you the global object, but it is more convenient to state it as follows. So you are just taking the following map, where morally it is just mapping this to gx and this to x. So, and this is just the action map times identity map. So if you want to discuss it, and the graph of the map is just the image row of times ID of G times X. So it is just the image of this map. Yeah, so one can ask sometimes about the property of this map, but so now we won't be interested about this, and what we need now is to notice that what is pre-image of the point xy. Yeah, so here you have a point xy, and the pre-image of it, so let us call it phi. So the pre-image of this point is just the elements of G, such that G X, yeah, so just G X is equal to Y, yeah? So and this is we called this transporter, and yeah, so actually
it's inverse, no?
yeah, actually it is inverse, yeah. So so we called this transporter because it was just a coset. Yeah, so this was so.
You write a subset of group, but set we are describing.
Yeah, so this is yeah, so this is a set of pairs. Yeah, so this is yeah, so y is fixed. Yeah, so this is pairs gy. Yeah, so that belongs to x, g times x, where x is equal to g of y. Yeah? So here you, so this is called the transporter, and this is just a coset. So transporter of x to y. And this is just a coset of stabilizer. Yeah, so this is just yeah, so this is G times gy. Yeah. So
Where G is a fixed.
just a second. I mean, so yeah. So this is yeah. So if yeah. So if you apply this to this one, yeah. So that you will get this one. Yeah. So if you substitute this element in here for this fixed G, yeah. So for this this choice of so of course you fix x and y. So this for fixed x and y, this will be if you take representative. So just G is some representative, representative G0 maybe. Yeah. So that x is equal to G0 of y. Okay. So this the dimension of this guy is so dimension of this fiber is equal to dimension of the coset, and dimension of the coset is of course equal to dimension of the stabilizer itself, because they are connected by the regular map, regular isomorphism. So you can map to one direction and the other, and have the just the dimension of the image is smaller. Yeah. So if you the dimension of the image is smaller than of the variety you map, so you have the equality of the dimensions, and then you see that so that this fiber, yeah, so the point corresponds to the dimensions of the stabilizer. So these functions, so this is precisely this function. But of course, so what you know, so what you get out of this, so applying we have the following theorem. So the function, yeah, so the set xk where dimension of the stabilizer raises, yeah, so yeah, so the set of points of x such that dimension of the stabilizer is bigger or equal than k, yeah, so is closed. Yeah. So you want to do the following, so let us prove it. Yeah, so considering this map, yeah, we see that considering this map.
Excuse me.
Question.
Like, when we are considering this phi of x, phi inverse of xy, it exists only if x and y go to the same.
Yes, I am the same orbit. Otherwise, it is empty.
Yes. So, but our like нижняя строчка expresses this as dim gy, which don't know anything about x.
Yeah, but I mean, so this is not equivalent. This is not equivalent arrow.
So
I mean, it is like division by zero somewhere, yeah? So, I mean, this arrow is exists if and only if G0 exists. Ну, то есть вы правильно говорите, но просто это вот тут как деление на ноль могло произойти, да? То есть, so this arrow uses, yeah, so uses the existence of G0. So, so this dimension is either empty, or so you cannot speak about. So dimension of the empty set, and then you can just use this G0. Yeah? So you have this map phi. Yeah, so we say that dimension of the preimage of any point, yeah, so is a semi-continuous function. So this set is closed. Yeah, so the set where so the set of the points x. Yeah, so notice that here you see, so here we precisely will write down it is in good words, yeah, because, yeah, so here if you are thinking about this map from the viewpoint of a variety y, so I shall write it down as the pairs of points gx, so this is just the set of the pairs of points gx in g times x, such that dimension of, so here I shall write gx and x here. Yeah. So this dimension is bigger or equal than k. So this is closed. Yeah. So closed by semi-continuity of theorem. Yeah? But this is, first of all, this set is located not where we want it to be located. And then this set has much additional, yeah, so I should, better I should have written this as, so just involving gx here, yeah, so like g0 here. Yeah? So, so this set is, has much junk. First of all, it has it contains not all the stabilizers of the point, but these transporters, and moreover, it lives on the different object. It lives on g times x and not on x. So let us reduce this. So of course, how to reduce it to stabilizers? So just we will just reduce it to the smaller subset. Yeah, so just we will take preimages of the same point. Yeah, so when you are taking preimage of the same point, it is of course just the preimage of this point is precisely stabilizer times x. Yeah. Okay, so as the subset in gx, yeah, and here you just consider the following. You yeah, so in order to reduce it to this, of course, you just take diagonal. And we assume that the x is separable, so this diagonal is closed in the product. So this is just, in order to reduce it to stabilizers, at least we just take the preimage of the diagonal.
Is this theorem applicable for separable lenses?
Yeah, yes, I mean it is all but speaking about algebraic variety, I am assuming this separability property. Non-separable.
Separable algebraic variety.
Yes, this is a famous example of the double line. So you are doing the following. You take the two copies. So in order to specify the algebraic variety, or what I mean, it is just algebraic set. Yes. So better to say. So I do not want to use the word scheme here, but just let me say that it is algebraic variety. However, in the future, I always want to assume that everything is separable that we study. So you have two affine lines, yeah? So then you have to specify the charts, yeah? So in order to do to glue something out of the affine varieties, you should, so they will play role of the charts, and then you you need to specify what is common intersection. Yeah, so here, so I can write it as U1 intersection of U2, and what is a common intersection here? I can write it U1 intersection, U2 intersection with U1. Yeah, so just in order to emphasize that a priori they are in the different objects. And then I want to identify them. Yeah? So I do the following. So for the subset, for this common open subset, I put A1 without 0. Yeah? And here I also put A1 without 0. And if you want to see what is isomorphism here, so there are two evident isomorphisms that you can use. Yeah? So one is just gluing it by identity map, and one is gluing by inverse map. Yeah? So if you glue it by, what is better from your point of view? Identity or inverse? Inverse, yeah. So because if you use identity map, if phi here is identity, then it will be a line with the so-called line with a double point, and it will look like this. So geometrically, it will be like a line, and if you want to, so if you move and take the limit that goes to the point, so how would do take limit on the variety that we are gluing out of some object? Yeah, so you are choosing the chart and taking limit there. Yeah. So and you can choose one chart. So for example, this one, and you will get to this point. And you may take this chart, and you will take the limit will be this point. So this means that the same curve has two different limits. And of course, this is what we don't want to have, which is, it is a little bit non-natural, and it is somehow shows that the space is non-Hausdorff somehow. So it is equivalent, not equivalent, but analog of this notion. And what?
What is a diagonal in this example?
A diagonal, you just have to pick. Yeah, so you are specifying it. The diagonal is just the pairs of product. The pairs of points, so they are like P1 times P1. Yeah? So outside it is clear, you just take the same copy of the point. But additionally, you get P1 P1 and P1 P2. P2 and P2. I mean, diagonal is defined almost I mean, as just said, theoretically, it is just this pairs of points. But one can show that it also should contain, so the closure contain P1 P2 and P2 P1. Yeah, so let me mark it as an exercise. If you cannot do it, just ask me later.
So we have more points in the closure.
Yeah, so then, so diagonal is just, you should think of it as set theoretically. Yeah, so here, so it is, I mean, it is not, so it's not how the proof should be organized, but you can here you can think of it set theoretically. But as I said, you can pass to the limit via using one direction. You can do it on one chart, and the other direction you can do it on the other chart. So these 2 points are obtained as the limit of one curve that is lying on the diagonal. Yeah. So yeah, and yeah, of course, if you why I was asking about inverse, if you get, if you take in inverse, what you get? Inverse map here. What variety will you get?
It will be projective.
Yeah, projective plane.
Line.
Line, yeah. So here we come to the point that this variety is closed. And notice that this maps surjectively on the diagonal, which is isomorphic to x. Yeah, so it maps to diagonal in x times x, which is, of course, isomorphic to x. So it is closed in g times x. And so you see that the fibers of this map are precisely the stabilizers. Yeah? So the fibers so just fibers of phi inverse of delta x to x consists of stabilizers of the point. Yeah? So it is isomorphic to stabilizer of the point. So this function is, yeah, so if you want to, so you know that intersection of this zk subset and this phi inverse is also the closed subset. Yeah, so it is the set of the pairs of points. So it is the subset of g times x, such that
This map, like, is projection or multiplication?
which one?
This.
This one, it is just mapping to diagonal, and then you can use the P1 or P2. Yeah, so just, yeah, so maybe I should write it like this. Yeah, so like delta x isomorphic to x. Just saying that it is isomorphic. So this is subset of g times x. Yeah, so that consists of the point gx such that. So this subset is actually isomorphic to just gx times x. Yeah? And this so this is a subset of g times x, where dimension of this set is bigger or equal than k. Yeah? So yeah, so this is a let me write it down. This is a subset where gx belongs to gx times x, and the dimension of gx, so of this set, so this is also isomorphic to gx, so dimension of the set is big or equal than k. Yeah, by assumption, so that we intersected with the key. So now we have to relate it with the stabilizer. So just take this zk tilde, I have denoted by this zk tilde, and intersect with a subset which is, of course, sits in every stabilizer. So this is a subset E times X. Yeah, so since so I take this subset, and I know that this this subset and maps actually via the action map, it maps surjectively, yeah? So to X, to and of course, so this intersection is non-empty and consists of the points if you, so you have to intersect each fiber with the subset, so it is just the points E times X, where the dimension of the stabilizer is bigger or equal than K. But this intersection, of course, identifies this as a subset of X. Yeah.
Why does the intersection ZK with phi minus that diagonal is not equal just ZK?
What?
I mean the upper intersection.
This one.
Yes. Why does it?
Yeah, because
So it means that we have some element from the pre-image that does not.
but zk is the copies. I mean, zk is here. Yeah.
Yes.
Yes. So zk is copies of two. So these are two elements such that the dimension of the fiber is bigger than k. So here you can take just here it consists of the coset of the stabilizer and the point. I mean, here the gx is not necessarily equal to x. Ну, то есть, как бы вот, когда мы ну, это вот и причина, что это не одноходовка задача. Ну, что, когда вы рассматриваете вот этот образ, да, что вы рассматриваете две точки, они друг друга переводятся элементом G, но они, вообще говоря, могут быть разные. Это просто две точки из одной орбиты. Ну, вот здесь. И понятно, что когда вы пересекаете с прообразом диагонали, вы говорите, что просто вот эти точки равны, вы делаете их равными. Да? То есть как бы тут, ну, как бы каждый шаг нужен. So this subset is closed, and this is precisely the set xk. So this is closed as intersection of two closed subsets, and the subset, this is equal to x key.
Can you remind how topology of product is constructed? It's not a product topology, but...
Yes, it's not a product topology, so let me discuss it a little bit. So, yeah, so actually this is the reason why separability is not equivalent of Hausdorffness. Notice that just what is Hausdorffness? It is just saying that in a topological space, any 2 points has non-intersecting neighborhoods, small open neighborhoods that do not intersect. Yeah? And in our case, so this happens since we are considering as the open subsets, we're considering just the complements to the closed subsets. So one can ask the question when the algebraic space is Hausdorff, but the answer is what? Yes, it is just finite collection of points. So in order to what is about topology? Of course, how do we introduce product topology in a usual setting? So in a usual setting, we take the open subset here, open subsets here, and take a product. Of course, this construction, of course, makes sense, but it's not what we want to get, because it even we know that on well, if you look at a affine space, so which is you can look at the A2 and try to consider the product topology. So if you consider the product topology, then what are closed subspaces? So the closed subspaces here are collection of finite collections of points or the whole set. The closed subspace here is finite collection of points or the whole set. So this means that if you look at product topology, the closed subsets will be a finite collection of points, finite collection of vertical lines, and finite collection of horizontal lines. And of course, it is not what we want to have. Yeah? So it's not a product topology that we expect. So we impose the condition that the product topology, so we introduce the topology on AN as the risky topology. And if you want to have a product topology on affine the product of affine varieties, you may just embed them in the corresponding product of affine spaces. So each of them has its own closed embedding. You have to prove that this is also closed embedding. And so it is defined by the system of polynomials here. And this is isomorphic to AN plus M. So you take the risky topology in this space, yeah, not thinking of this as a product. So if you want to define the product topology on more general space, you just have to understand that if you have covering of via the chats UI, Y is covered via the chats VI, VJ, then you just have to take all different, so you know how to glue them in the product because you know how to do it theoretically. And you just know how to define topology on the products of the charts. Yeah? So you know how to define here via, because the charts are taken to be affine, you use this property, and then you glue it, and you say that the subset is closed if so X times Y is a union of products, and you use the following criterion that says that if you want to check that something is closed, is inside X, which is a union of UI is closed, if and only if intersection of Z with UI is closed. Or the same, you can do it with open subsets, doesn't matter. Okay?
Can you repeat what
Yeah, so just we can, so having this variety, you just, it is closed, yeah? So you can just intersect it with zk, so with this subset which is closed by semi-continuity. And so you get this zk tilde. And this, you look at zk tilde, and you just write down what it is. Yes, so this is, since you intersect with so this is a collection of pairs of gx. First of all, gx has to map on the diagonal. So this is consists of the pair point from stabilizer and fixed point x. And you assume the condition on zk, so it is just the dimension of the fiber bigger than k. So you look at this object, it is a fiber, precisely the fiber of the point. Yeah, and so notice that here, yeah, so I should have written, I stated it but I should have written that, so since here we described the fiber as the transporter, so it is just the g0, gy times y, so the fiber over this point, it is here for transporter, it is like this. And if you want the fiber for this one, yes, so this is isomorphic to the fiber over the point, it is just gx times x. So the condition for the dimension of the fiber is, since this fiber is isomorphic to gx, so the condition on the dimension of this fiber is rewritten as the condition on the dimension of the stabilizer. Yeah? And then you intersect this subset with e times x. Единица, да. Ну, единица в группе. So identity in the group. So you intersect it with this set, and notice that stabilizer, it's always have a e inside it. So you do not lose any information. In the same time, this intersection is equal to e times x, precisely. Yeah? So this a collection of points of, so this is collection of points of x. So this is just intersection of gx times x with e times x. And this is precisely the collection of, so if you intersect zk, so you are intersecting this subset with this one, and you write down this condition. Yeah, so this intersection is just a point x, and the condition is that this dimension is bigger or equal to k.
Is zk intersected with e times x equal to zk tilde intersected with this? So
Yeah, yes, I mean you can do it in. No, I mean you have to.
I don't need intersect with diagonal.
Нет, нет, ну конечно, нет, конечно нужно, потому что чтобы вот сюда попасть. Не, ну вы просто как бы so just in any orbit you can so this is like so you have to specify the set where you are taking stabilizer, not transporter. Ну вы говорите, что в другом классе нету E, ну да. Yes, yeah, so in the different class you do not have E. Yes, so there is no need actually, yeah. I mean, you can do it by this step, but at least this is more comprehensive, maybe. I mean, yeah. You are right, because since but then you have to notice this, yes, so that transporter doesn't have E. So it doesn't intersect, yeah, so the remark.
That just said theoretically intersection.
Yeah. So, so remark, which is good, yeah, so that this, the xk is just obtained of intersection of the k with e times x. And the reason for this that if you if you take this gy times y and intersect it with copy e times y, then just, I mean, if you intersect it with e times x, yes, so you get that the condition that this is, of course, will result that E belongs to G0 of Y, but this is non-possible for non-trivial G. So but this implies that G0 is equal to E since...
Not equal, but belongs to...
Yeah, so... Yeah, belongs to... yeah, so this means that G0 belongs to stabilizer, since this is only coset containing E. Okay.
But if you consider ZK tilde, can we say that xk is just projection on x?
No, it's different, yeah, because so there are more. I mean, there are more points.
I think that this fact that the xk is the k-intersected with something is like... Is it obvious?
Which one?
Definition. This remark that xk can be easily obtained from...
This one?
Yes.
I just have written the phi bar.
No, is it from just definition? Or
It's from just definition. I mean, it is just...
say this to her, but maybe it's the other thing.
Не понял. Ну, в смысле, ну просто вот это пересекаете с этим, ну как бы. Ну, вот это слой над y, ну вот этот слой над y.
Это просто сложно.
Не, ну я просто как бы добавил условия, ну, на размерность. Ну, как бы вот пересек, чтобы добавить условия на размерность. Так, конечно. Я сказал, что это просто, ну, как бы... Что сложно в том, что g на x мы здесь не в x сидим. Ну, как бы, что вот это подмножество находится внутри g на x, а не, ну, как бы, поэтому мы еще должны как-то перейти к самому x.
Ну, вот мы перейдем к самому.
Ну, вот мы перешли, да. Ну вот. Не, она просто обсудила, над какими точками какие стабилизаторы, и все. Ну, что над диагональю просто у нас лежат стабилизаторы. А если вот так пересечь, то как бы все равно мы попадем в стабилизатор. Ну, это теоретико-множественное доказательство фактически. Ну, как бы тут надо помнить только, что ну, пересекли замкнутое подмножество с замкнутым. Ну, как бы вот и все. Просто. Okay. So, this is about semi-continuity of fibers. Yeah, so this can be also one can also notice that so we have specified explicitly the one can also discuss the no, I don't want to say this. Yeah, so this is quite important property. This, for example, shows that the maximal dimension of the orbit appears on the open subset. Yeah, so that if you search for the orbit of maximal dimension, if the orbits of maximal dimension, the orbits of maximal dimension cover the open subset of X. Form the open subset. Ну, образуют орбиты с максимальной размерности, образуют открытое подмножество X.
Now let's write about each orbit forms itself. So, union of orbits. Union of orbits of maximal dimension. То есть орбиты максимальной размерности покрывают открытое подмножество. Образуют открытое подмножество.
То есть у нас есть теорема полунепрерывности.
Да.
Берем k равное максимальной размерности, получаем, что это множество замкнутое. А теперь...
Множество, где стабилизатор максимальной размерности.
Да, это наоборот.
Поэтому это орбиты ведут себя наоборот, да?
Стабилизатор имеет минимальный размер.
Да, so this is where this is the set where stabilizer has a minimal dimension. Has a minimal dimension.
So stabilizer has dimension great one if L's are closed.
Yes. Yeah. So this we take minimal dimension and take minimal dimension plus one. Yes. So this is a complement to the set, complement to the closed subset. X L plus one. Yeah?
Why is there maximal dimension? Is it true for maximal dimension plus maximal dimension minus 1?
Union of orbits.
Yeah, union of
Of course it is.
Не, я не понял, что.
Смотри, тут утверждение, что объединение максимальной размерности открыто, значит, что объединение орбит максимальной размерности плюс орбиты максимальной размерности минус 1 тоже будет открыто.
Да, конечно.
Размерности больше.
Ну, если вы... So if you take the orbits of maximal dimension and add the next family of orbits of smaller dimension, will be also open subset.
So we can just take all dimensions of all orbits of the dimension was included.
Yes, yeah. So this tells us that, so also one can ask about the following. So this is dimension of the orbits, but usually you want to say that we are considering, in topology there is a factorization map that says that you can identify, consider the equivalence classes and factorize by this, contract all these equivalence classes and the points. So you have the space which parameterizes the orbits, at least topologically. In algebraic geometry, we do not have this a priori. And one can ask about the dimension of the space or the number of parameters that you need. And so this is quite tricky question, because it can happen that for general orbits, so you need so the set of parameters, so the dimension of the set of parameters of the set of orbits, just the dimension of the quotient, this is called quotient. So the dimension of the quotient so I shall put it in the parentheses, because it is like if you do not have quotients, what we are talking about. So the dimension of the quotient is dimension of x minus dimension of orbits of maximal dimension. So that just g of dimension of the orbit of maximal dimension. So it is just the number of parameters that you need to parameterize the orbits in the open subsets. And it can happen that sometimes this set is so one can ask how this number behave when you pass to some closed subset. So how this number behave when you pass to closed subset, G invariant subset. So and it happens that it can happen, for example, that you have open orbit some of the group, and the complement, if you pass to the complement, it also have open orbit. So it can happen that X has open orbit and Y has open orbit. So this, for example, so this is, for example, multiplicative action on A1. Of course, it seems to be trivial, but nevertheless, so on A1, you have orbit of maximal dimension. On the open set, when you pass to the closed subset, there is also one orbit.
So there is the question like when algebraic variety can distance open subsets?
So sometimes, for example, algebraic variety has only finite number of G orbits. So, and it can happen that this Y has quite a lot of orbits. So it can happen that X has open orbit, and Y has infinite number of orbits. Y has infinite number of orbits.
Why it is quotient? What is Y? What?
Is a subset. I mean, you take X, yeah, so the variety, and you consider the following problem. You consider expected dimension of the quotient. So the expected dimension of the space that parameterizes the orbits. And on the open so this on the open subset, the orbits has maximal dimension. So the idea is to look at the open subset and try to find quotient there. And the dimension, so expected dimension of the quotient is the dimension. So since just a posteriori you want to map X to what you will call quotient, such that the orbits, if you think of topological space, yeah, so you are getting a quotient that's characterization by equivalence relation that orbits impose. Yeah? So the 2 points are equivalent if they lie in the same orbit. Yeah? So this means that if you want to write down what you want to call quotient, this is just a map from x0 to z. So this, I assume that it exists on some open subset. So we call this quotient if P consists of preimage of z, consists only of one orbit. Yeah? Consists of one orbit. This is ideal situation is that it occurs not very frequently, but I mean you have to work to be able to say something about your situation, what you have. So if you have this map, I mean assume that, so this from this point of view it will be the topological quotient where it corresponds to equivalent classes of factorizing by equivalence relation that 2 points are in the same orbit. This says that you have, this should be restated as that you have the morphism of algebraic varieties, where Z is algebraic variety and preimage consists of one orbit. Then you can speak about the theorem on dimension of fibers, and dimension of x0 is equal to dimension of general fiber and plus dimension of z. Yeah? So z sits in some open subset. And so this means that the expected dimension of the quotient is just a dimension of x0 minus dimension of the preimage.
What's the definition of Z?
Z is just the following. This is the algebraic variety. So we say that Z is a quotient. If you have map, if it is algebraic variety, you have a map from x0 to Z, such that preimage of Z consists of one orbit.
Of whole orbit, you mean?
Of the whole orbit. Ну, то есть, как бы, мы, Z это уже многообразие.
It's like set of orbits, but with some
Yes.
like structure.
Yeah, so we want
We
to...
only want for this to be more.
Yes, yes.
And we don't pay attention to the dimension of orbit. So we just glue orbits on any dimension.
Yes.
What's this circle?
What?
X is 0.
Gx. It is just, I mean, you cannot expect this on the open subset. So I put 0 just. You cannot expect it to be on the whole subset, on the whole set X. So I have put 0 to emphasize that it happens on the open subset.
So for any open subset, we consider only orbits in this open subset, and then call this a quotient of whole X. Or no?
Yes, I mean you can call it the quotient of all X. I mean it is what you want to expect, but I mean it is the situation that is just that could come from topology. It is I mean from naive point of view. And but of course later we shall specify this precisely what I mean by this.
There can be no such pi.
Yes, generally there will be no such pi, even on the open subset. So, yes, yes. So you should specify what you want to get. Yeah. So so this is a slight problem, but you can speak about expected dimension. Yeah, so that the expected dimension is the dimension of this parametrizing space, and this is just dimension of X minus dimension of orbit from the open subset. And for example, if the orbit is from the whole, just if you have open orbit, then this difference is 0. Yes, so the open orbit, it is just, so the quotient is just 1 point. Yeah? So this, and what I wanted to say that one can think that if you have some problem, and you consider some equivalence relations, if you have this property just for that, if you think of the number of the parameters you want to classify the problem, yeah, so classify the orbits, so the open subset is more important for us. The orbits from the open subset is more important for us, and they will have the largest number of parameters that just in the picture. But it is not true. So the example is the following. So consider the action. And about this example you all know, of course. So the example is the action of GLM on the set of matrices, on matrices n by n matrices. Just you take the matrix here, you take element G here, and you multiply the matrix. So what is the generic orbit in this set? Какая? А? Не, ну в смысле, что если матрица максимального ранга, тогда что?
A is not of maximal rank.
If A is of maximal rank, then what?
Maximal rank, then J is transitive.
Yes, then you can map any basis to any basis, yeah? And then you said precisely what is needed, yeah? So that if what is important here is the rank of the matrix, yeah? So if rank decreases, but if the matrix is of the smaller rank, yeah, so can you map any matrix of smaller rank to the matrix?
Yes, it's something like continuation of.
Ну как? Вот, например, можно взять матрицу ранга, ну поставить вот тут нули, а тут какой-то вектор. Не, подожди, да, вот именно, что надо с двух сторон действовать. Вот. А если вы просто возьмете тут просто пропорциональные векторы, то они действием, диагональным действием, ну, столбцы, да, то они Это тоже и то матрица ранга 1. Yeah, so if you take all the columns, 0 columns and 1 non-trivial column, it is a matrix of rank 1. If you take the collection of the same vectors, then of course when you apply matrix, it will be it will map to the matrix of the same form. So this is never in the orbit of this one. Yeah? So it is.
Multiplication from the left is the linear transformations of rows of matrices.
Yeah. Нет, слева это вы действуете на базисных элементах. Ну да. So this shows that and of course how to describe this orbit. I mean, how many parameters do you need for rank 1 matrix? Но если вот у вас есть набор векторов, и у них есть линейная зависимость, то при действии, so you can think of this as the collection of vectors. So matrix is collection of n vectors, and you apply the element of G, V1, Vn. Yeah? So this means that if you have linear dependence between these vectors, if you apply G, this linear dependence will be preserved.
So answer is that there is like for each vector of coefficients its own orbit.
Yeah. So if the matrix is of rank 1, yeah, so you take one vector and so it looks like K V1, K1 V1, K2 V1, etc. K AVN. Huh? Yes, so it is n minus 1 dimension.
N minus 1 dimensional.
Because you can multiply by the number.
Closed set.
Yeah. So so maybe a good exercise is to so let me state it. Describe the set of orbits of GLN on matrices, and give the dimensions. So dimensions, the number of parameters you need. So in which closed subsets they can be put, and which numbers of what is the number of parameters.
There is n-dimensional, n-1 dimensions for parameters. What is the dimension of stabilizer?
What?
Here is an equation between the dimension of stabilizer and dimension of the number of parameters.
No. Because I mean, for the reasons for these examples, I mean, yeah. So, for example, you can have the property that you have only finite collection of orbits. Yeah, and so this the rank can help you, and maybe it is a good just observation that was done. That maybe it is helpful to consider this subset, so the set of GLN and GLM acting on the matrices of m times n matrices. So on one side from the right and on one side from the left, yeah. So notice that these two actions, they commute. Yeah. So if you take, this will help you to understand how the matrices, which orbits lie in the same family. So that it is natural to say that you can take the orbits and so one orbit in the family, for example, of rank 1, and try to act by this group. Yeah? And then you get a collection of other orbits. So maybe it is a good point to make a break. Let us make a 10 minutes break, and we shall resume to your question of the day.